Hi, this is John Whitaker for the Probability 1 class, and this is our 14th video lecture. And we left off last time talking about moment-generating functions. And so we want to do a little bit more in terms of calculating moment-generating functions for a few more random variables. And so I want to start off with the fact. It says, let x be an exponential random variable with parameter lambda. Then the moment generating function MGF of x is phi sub x of t equal to lambda over lambda minus t for t being less than lambda. Okay? So that's what it's defined for. All right? And we want to prove this fact. Okay. So here we start off with let x be exponential with parameter lambda. Then when we compute the moment-generating function, phi sub x of t, remember it's defined to be the expected value of e to the tx. And an exponentially distributed random variable is a continuous random variable. So this is the expected value is an integral from minus infinity to infinity of e to the tx f of x, the PDF of x, dx. Now, if you remember, the PDF for an exponential random variable, what it's equal to is it's equal to lambda times e to the minus lambda x for some lambda that's greater than 0. That's what we're assuming your lambda is. And that's what it's defined to be when x is greater than or equal to 0. And it's 0 otherwise. So that adjusts this integral to be an integral from 0 to infinity of e to the tx. This would be lambda e to the minus lambda x dx. Okay. Then here we can combine the e terms to get, and I'll pull out a lambda. We're having an interval from 0 to infinity of e to the, I'll write it down as t minus lambda times x dx. And this is an integral of e to the something. We can integrate e to the something as long as we have the derivative of the something listed in the integral. And the derivative of t minus lambda times x with respect to x is t minus lambda. So I'll rewrite this as lambda over t minus lambda, integral from 0 to infinity of e to the t minus lambda times x dx, which is equal to lambda times t minus lambda. Okay. And here, this would be e to the t minus lambda. I'm sorry, let me write it down with an integral. Integral from 0 to infinity of e to the t minus lambda times x times t minus lambda dx. Okay? That's where I am. So I can integrate this at this point. Okay. That's equal to lambda over t minus lambda. And then that integral was e to the t minus lambda times x, and we will evaluate that as x run from 0 to infinity. Okay. Now, when you think of x getting really, really big, if this t minus lambda is positive, then you'd have a positive number times something hugely positive. Any hugely positive number will go to infinity. So that integral would not converge, it would diverge. So what we need to have is that this part needs to be negative. And so what I'll say is when it is negative, and when that happens is when t is less than lambda. So over here to the side, I'll say t has to be less than lambda. We get, so that we have convergence. We have lambda over t minus lambda. When I stick in a huge positive number, bigger and bigger positive numbers, and multiply by a negative number, that's what happens when t is less than lambda. Then this part goes to 0, minus what we get when we let x be 0, which would be e to the 0, which would be 1. And so here, this ends up being lambda, and I'm going to have t minus lambda times minus 1. I'm going to apply the effect of the multiplication by minus 1 to the bottom to get lambda over lambda minus t, where, or when, t is less than lambda. And that's what we said. So that ends this proof. Now what we want to do is we want to check to make sure that the characteristics for an exponential hold true when we use the moment generating function to check them. And so in particular, if we have, so I'll say note, if we take a look at the derivative of this random variable, exponential random variable with respect to t, what we're going to have here, well, let me just write this down before I take the derivative in a nice way for how I can take a nice way with respect to taking the derivative. So here, if I want to take the first derivative now of this moment generating function, it's a constant times something raised to the power. So I write down the constant, I write down the power, I write down the something to 1 less power, using the chain rule extension of the power. So 1 less power, and then I take the derivative inside. With respect to t, the derivative of what was being raised to the power, this will be minus 1. And so here, this minus 1 and this minus 1, of course, make 1. We have lambda over lambda minus t to be squared. And so the expected value of x is this derivative evaluated at 0, when t is equal to 0. This ends up being lambda over lambda squared, and that's just 1 over lambda, which was the expected value of an exponentially distributed random variable. That checks out. And now, if we take the second derivative, so phi double prime of t in this case. Okay, here, let me just rewrite p prime for a second in a nice form. So it's lambda times lambda minus t to the minus 2. So the second derivative, that's going to be equal to lambda times minus 2, lambda minus t to the minus 3 times minus 1, which equals to, this will be 2 lambda over lambda minus t to the third. So, when I take the second derivative and evaluate it at 0, we get 2 lambda over lambda to the third, or 2 over lambda squared. And that is the expected value of x squared. So the variance of an exponentially distributed random variable, don't forget, it's the expected value of x squared, which is 2 over lambda squared, minus the expected value of x to b squared, which was 1 over lambda to b squared, so 1 over lambda squared. And that is 1 over lambda squared, which was the variance of an exponential. So it checks out using the moment generating functions. The last one I want to do in terms of the moment generating function for is that of a a normally distributed random variable. So here's a fact. If x is normally distributed, with parameters mu and sigma squared, then the moment generating function of x is phi, so x of t, and it's equal to e to the mu t plus sigma squared t squared over 2. So this is the power of e. We want to prove this. So let x be normally distributed. With parameters mu and sigma squared. Then we're going to do, first of all, if you will, case 1, that mu is equal to 0 and sigma squared is equal to 1. Okay, so x is standard normal. That's the case we're looking at. And let's call that z. And so we'll find the moment generating function of the standard normal as our first case. Okay, so phi sub z of t, that's going to be equal to the expected value of e to the tz, let's write down the z kind of this way, which is going to be the integral from minus infinity to infinity of e to the tz times, well, I'm going to pull out that constant of 1 over the square root of 2 pi out in front. And then it was e to the minus z squared over 2 dz. Okay. We can rewrite this as 1 over the square root of 2 pi, integral from minus infinity to infinity. I'll say this is e to the, well, it's t, let me write it down this way, minus the quantity z squared, and then plus 2, well, it'd be minus, because I factored out a minus 2tz all over 2 dz. Now, completing the square, on the quantity z squared minus 2tz, we have that this would be equal to, it's z squared minus 2tz. So what you do is you take half of this number, what's out front of the quantity out front of z, and square it. So half of this is a minus t, so you square it. So you put a plus t squared, okay? And then you would have to subtract t squared, okay? That's what we have. So, so that's what I'm doing. So this integral becomes 1 over the square root of 2 pi, keeping it what it is, minus infinity to infinity. E, and I'm going to rewrite this, is minus, and so here it's going to be z squared minus 2tz plus t squared, okay? This is over 2. And so really I have added a t squared in parentheses, multiplied by minus 1. That's minus t squared. It's still over 2, so I'm going to have to have plus t squared over 2. Okay. Now, that's going to be equal to, can be rewritten as 1 over the square root of 2 pi, and from minus infinity to infinity. Here this is e, and we can rewrite this as minus, so it's a perfect square. So it's z minus t to b squared over 2, and then here this is going to be times e to the t squared over 2. Remember, we're integrating with respect to z. I forgot to write down that dz on the last integral. Okay, the e to the t squared over 2 can be taken out of the integral because it's constant with respect to z. So we have 1, or e to the t squared over 2, 1 over the square root of 2 pi, integral from minus infinity to infinity, e to the minus quantity z minus t squared over 2 dz. And we need to concentrate on this integral part, including the 1 over the square root of 2 pi. What that is, it is, forget the integral just for a second, just the 1 over the square root of 2 pi times e to the minus z minus t to b squared over 2. That is the PDF of a normally distributed random variable with parameters t and the sigma squared equal to 1. And so when you integrate it, you get 1. And so this is going to be equal to e to the t squared over 2 times 1, which is equal to e to the t squared over 2. Okay. So the moment generating function for a standard normal is e to the t squared over 2. Now, case 2. Is suppose mu is not 0 or sigma squared is not 1. Then we can rewrite our previous pattern, x equal to sigma times z plus mu. That's what it's got to be. And so we want to take the moment generating function of that, find the moment generating function of that random variable x. And so phi of x is going to be equal to the expected value of e to the t x, which is going to be equal to the expected value of e to the, well, it would be sigma times z plus mu, which equals to the expected value of, let's write this down, e to the mu times e, oh, I forgot the t, excuse me. Okay, so this is e to the t, mu t times e to the t sigma z. Okay, and then this is going to be equal to e. Now remember, here we'd be integrating with respect to z. So in terms of our integral, this is a constant, so we can pull it out. So this is e to the mu t, it's a constant here, xt, times the expected value of e to the t sigma z. And so this second part is the moment generating function for a standard normal evaluated not at t, but at t times sigma. So this is equal to e to the mu t, and then this will be, remember the moment generating function, so let me write it that way. So it's phi sub z evaluated at t sigma, which is equal to e to the mu t. Now remember what this was. It was e to this evaluation to b squared over 2, and so that's going to be equal to, let me write it this way. So phi of x of t, what we're working with, is going to be equal to e to the mu t plus this part, which is t squared sigma squared over 2. And that's what we said it was going to be.
That's the answer.
Sir. Let's check the characteristics for a normally distributed random variable using the moment generating function, namely its expected value and variance. So note if x is normal with parameters mu and sigma squared, phi of x of t we just found was e to the mu t plus sigma squared t squared over 2. So if we take this moment generating function's derivative, we get e to the mu t, we're taking the derivative with respect to t. So taking its derivative, right, it's equal to something, write down equal to something, times the derivative of the power. The derivative power would be mu plus, well, it'd be sigma squared over 2 times 2t, so that'd be sigma squared t. And so the expected value of x, which is nothing more than the first derivative of the moment generating function evaluated at 0. Here, this is going to be 0. That part's 0. This is 0. It's e to the 0, which is just 1. Here, this is going to be mu. This is going to be 0. So we end up getting mu, which is the expected value. Now, t double prime t is going to be the derivative of this, so we're going to have to use the product rule. So I'll write down the first times the derivative of the second. The derivative of this with respect to t is just going to be sigma squared plus, now we'll write down the second, times the derivative of the first. The derivative of this guy is nothing more than e to the mu t plus sigma squared t squared over 2 times the derivative of this power, which is exactly here, so it's this guy squared. So I think I got room now right here. Phi double prime sub x of 0. So if we let t be 0, again, this is part's going to be 1. This is sigma squared plus this part is going to be mu squared. And here, this is going to be e to the 0, so that's just 1. So we get mu squared plus sigma squared. And that's the expected value of x to b squared. So lastly, to get the variance of x. Remember, that's the expected value of x squared minus the expected value of x to b squared. And so that's going to be equal to, we have mu squared plus sigma squared minus, this was mu squared, which equals sigma squared. And that is the variance of the normally distributed random variable. Okay. All right. Here's a fact that says if x and y are independent independent random variables. Then the moment generating function of x plus y, that's going to be phi, so x plus y of t, what that's going to be equal to is phi, the moment generating function of x times the moment generating function of y. We won't prove that, not so bad. Okay. So, to prove, we let x and y be independent random variables. Then the moment generating function of x plus y is phi sub x plus y of t, which equals to the expected value of e to the t times x plus y, which is equal to the expected value of, here we would have e to the t tx plus ty, and I'm taking my time here, which is the expected value of e to the tx times e to the ty. Okay, we're taking the expected value of a function of x times a function of y, where x and y are independent. And so we had a fact that said that's the same thing as the expected value of the first function times the expected value of the second function due to independence. But this right here is nothing more than the moment generating function for x times the moment generating function, the second guy is the moment generating function of y. And so that's the proof. I want to state another fact without proof that's going to help us use some examples, justify something we said earlier. And that fact is the following. It says, there exists a one-to-one correspondence between the moment generating function and distribution of a random variable x. So what this is saying is, if you know what the moment generating function is, you see it, that goes to a particular type of random variable. And let me write this down. This means the moment generating function uniquely classifies the random variable type You might remember we had listed a fact previously about the sum of binomial random variables that were independent. We said that the result was a binomial random variable with certain parameters. And we said the same, in that same fact, we said something about if we had two independent, normally distributed random variables with certain parameters, if we added those together, we get a normally distributed random variables with the parameters being the sum of the first two plus the sum of the other two, the other random variables involved, or the random variables involved. I'd like to look at those situations again. So, as an example, let's let x and y be independent binomial random variables. With parameters n and p, so n and p go to x, and m and p, parameters going towards y. Then, let's look at phi sub x plus y of t. Well, that's supposed to be equal to phi sub x of t times phi sub y of t because of the independence. And so here, this was the moment generating function for a binomial. Okay, so here this one has n. So it was p to the et, I think, minus p plus 1 to the n. And then this guy is going to be, its moment generating function for y is p to the et minus p plus 1 to the m. And that's equal to p to the et minus p plus 1 raised to the n plus m. And here's what I want to tell you. This is the moment generating function of a binomial random variable with parameters it's m plus n or n plus m and p. And that's what we had as a conclusion. Okay? So the moment generating function's form is the moment generating function form for a binomial with these parameters. So that's how we're using the previous fact that I just written. And now let's look at an example where we have two independent, normally distributed random variables. So let x and y be independent, normally distributed random variables. With parameters mu sub 1 and sigma squared, sigma sub 1 squared, and for y we have mu sub 2 and sigma sub 2 squared. Okay. Then the moment generating function for x plus y is phi sub x plus y of t equaling phi sub x of t times phi sub y of t. And that's going to be equal to, if you remember, we just did this today, this lecture. This is e raised to the m sub 1t plus, so is the power, it is t squared times sigma sub 1 squared over 2, and then times e sub mu sub 2t plus t squared times sigma sub 2 squared over 2, which we can rewrite as being equal to e sub mu1 plus mu2 t plus, this would be sigma 1 squared plus sigma sub 2 squared times t over 2, and that is the form for a moment generating function of a normally distributed random variable. So I'll write that down here. So, x plus y is normally distributed with parameters, it's mu sub 1 plus mu sub 2 and sigma sub 1 squared plus sigma sub 2 squared. The next thing that I want to do, kind of the last thing that we're going to do in this chapter 2 of our book, is we're going to look at something called limit theorems. So these are statements involving random variables, and the first one, so these are limit theorems. Top. And so the first one is called Markov's inequality. And here's what it says. It says, let x be a non-negative random variable and a be some number greater than 0. Then the probability that x is greater than or equal to a, that quantity is going to be less than or equal to the expected value of x over a. I'm going to prove this. Okay, so the proof, we're going to assume that x is non-negative. Random variable. And a is greater than 0. Okay, to get the result that we want, we're going to define a new random variable. We're going to define I to be equal to, it's going to have two output values. One, if we're in the case where x is greater than or equal to a, and it's going to be 0 if otherwise, the random variable x. So this is a big X. Okay? So that's I. By the way, the proof that I'm giving here is different than what is listed in the text. Okay? So here's what I want you to notice, or I'll write a claim first. The claim is that I, it's a random variable, so it's a function, but for any particular input you give me, it's going to be less than or equal to x over a evaluated at that same input value. Okay? And so I want to do the proof of this claim. Okay, so here's what we notice. If we have two cases, so case 1, that is that x is greater than or equal to a, then we know that I is going to be equal to 1. Okay? So if x is greater than or equal to a, I is equal to 1. Now note that x divided by a is going to be greater than or equal to 1. Here, I'm just dividing everything by a. So we get that I, which is 1, this will have a place, is going to be less than or equal to x over a. Okay. The other case is if x is less than a, so it's got to be bigger than or equal to 0. Then, in this case, I is going to be equal to 0 by its definition. Okay. Now, note, if I divide everything by a, I'm going to have that 0 is less than or equal to x over a, and that's because x and a are both positive, so that's what I get. So in this case, I is going to be less than or equal to x over a. So it's true in all cases. So that ends the proof of claim. That is, that we know that I is always less than or equal to x over a. So, since I is less than or equal to x over a, so I'm not going to say too much about this, but look, the output values for this guy are always less than or equal to the output values of this guy. So if you take the expected value of this guy, it's going to be less than or equal to the expected value of the right-hand side. Okay. Thus, we have that the expected value of I is less than or equal to, well, the a is a constant, and so this ends up being the expected value of x over a. Okay, you can just think of this as 1 over a times x, where you can pull out the constant. And so that's what we have. Now, here, remember what we're trying to show. We're trying to show that the probability that x is greater than or equal to a is less than this quantity. So, what is this expected value of I? So, since I is discrete, the expected value of I, it's equal to, so I'll write right here, is the sum over all output values for I, but I can only be equal to 0 or 1 of I times f of I. Well, when I is 0, you just get 0. When I is 1, you just get f of 1. So that's the probability that I equals to 1. And when does I equal to 1? Well, the only time that I equals 1 is when x is greater than or equal to 0, greater than or equal to a. So that's the same thing as probability that x is greater than or equal to a. Okay, so I put in for the expected value of I that that's the probability that x is greater than or equal to a, and we get the result. So let me write that down. Is less than or equal to the expected value of x over a. And that's what we're trying to do. I want to go ahead and state and prove another limit theorem, and that's called Chebyshev's inequality. So it says let x be a random variable with finite mean, that's the expected value of x, equal to mu, and variance, the variance of x equals to sigma squared, and let k be greater than 0. Then, so this is for any k, then the probability that the absolute value of x minus mu is bigger than or equal to k, that's going to be less than or equal to sigma squared, the variance, over k squared. And we'll prove that. Okay. So, prove, we go on the left, x be a random variable with the expected value of x being mu and variance of x being sigma squared. And k be greater than 0. Okay. Now, the first thing I'm going to do is a claim. And the claim is that the absolute value of x minus mu is going to be greater than or equal to k if and only if x minus mu to b squared is greater than or equal to k squared. Okay, let's prove this claim. So here, it's an if and only if statement, so we'll go in this direction first. So we're going to let x minus mu inside absolute values be greater than or equal to k. And remember, k is greater than 0. So the absolute value of x minus mu is nothing more than the square root of x minus mu squared underneath here. Is greater than or equal to k, is greater than 0. Now, what I want to do is, since f of x equaling to x squared is increasing on 0 to infinity. So I'm thinking if this is a guy in 0 to infinity, this is a guy in 0 to infinity. If we apply f to that, it will maintain inequality. So that means that the square root of x minus mu b squared is going to be greater than or equal to k squared. So, that says that x minus mu to b squared is going to be greater than k squared. And that satisfies that one direction, so of the claim. So going backwards, we're going to let x minus mu to b squared be greater than or equal to k squared. Now, here, these are always going to be greater than 0. So since f of x equaling to the square root of x is an increasing function, then it's going to maintain this inequality. So if you will, the square root of k squared is going to be less than or equal to, that's right, the square root of x minus mu to b squared. And so the square root of k squared is k because k is positive. is going to be less than or equal to, this is the absolute value of x minus mu. And that proves, that's the end of the proof of the kind. So here's what we're looking at. We're looking at the probability that the absolute value of x minus mu is bigger than or equal to k. Okay? That's the same thing as the probability that x minus mu to be squared is greater than or equal to k squared. And so note, x minus mu to be squared is a non-negative random variable. So we can apply Markov's inequality. So applying Markov's inequality, we have the probability that absolute value of x minus mu is bigger than or equal to k, which is the same thing we just said, is x minus mu to be squared is greater than or equal to k squared. Okay, I'm applying Markov's inequality. This is going to be less than or equal to the expected value of this random variable, which is x minus mu to be squared, over this guy, which is k squared. But that top is nothing more than the variance of x over k squared, which is equal to sigma squared over k squared. So as a conclusionary statement, we have that the probability that absolute value of x minus mu greater than or equal to k is going to be less than or equal to sigma squared over k squared. And that's the proof. Ladies and gentlemen, we'll stop there. Next time we'll begin by rewriting these two inequalities, these Markov's inequality and Chebyshev's, and do an example of them. Okay. Thank you very much.